Hey, welcome to the Explainer. Today we're going to crack a code that's hidden in plain sight behind one of the most common and honestly elegant shapes you see every single day. Let's dig in and find out what its secret is. You know when you see a basketball swish through the net? Or even just the gentle curve of a satellite dish? Have you ever stopped and wondered, what makes that shape so perfect? It feels so natural, right? Well, believe it or not, there's a secret code behind it all. And it's not just a basketball. I mean, look at a suspension bridge. It's that same beautiful curve, what we call a parabola. And that is absolutely not a coincidence. It's all math. So what is this hidden code that's literally all around us? All right, section 1, the curve's secret code. Now the secret, it's not some crazy ancient mystery. It's actually just an equation. And today we're going to break it down piece by piece so you can see exactly how it works. And here it is, the moment of truth. The secret is the quadratic equation. Yep, this is the master key, the blueprint that both nature and engineers use to create those perfect curves we've been talking about. Okay, section 2, anatomy of a quadratic. So what even is this thing? To really get it, we've got to look under the hood. Let's break down its anatomy and see what makes it tick. Okay, first things first, that name, quadratic. It sounds a little fancy, but it just comes from the Latin word quadratus, which means square. And honestly, that's the big giveaway right there. It's called that because the main variable, usually an x, gets squared. You'll always see that little x squared. That makes it an equation of degree 2, which is just a mathy way of saying the highest power you'll find is a 2. Now, every single quadratic equation out there can be dressed up in this one universal outfit, the standard form. ax squared plus bx plus c equals 0. Think of this as its official ID card. It's the blueprint. So in this blueprint, the a, b, and c, they're just numbers. They're like the settings, They control the shape of the curve. Like a decides if the curve opens up like a smiley face or down like a frowny face. And x is the big mystery, the unknown value we're trying to find. But here's the one golden rule, the most important part. A can't be 0, ever. Because if a is 0, that whole x squared part just vanishes. And poof, it's not a quadratic anymore. All right, section 3, spotting equations in disguise. Now here's where it gets kind of fun. These equations don't always show up looking all neat and tidy. Sometimes they're in disguise, and you have to play detective to figure out what they really are. So take a look at these. They look a little chaotic, right? A total mess. But honestly, with just a little bit of simple algebra, like just shuffle all the pieces to one side of the equal sign, they snap right into that clean, standard form we just talked about. And once they're all organized, bam, you can easily pick out your A, your B, and your C. So, section 4, cracking the roots. Okay, we know what a quadratic looks like, and we know how to spot one even when it's hiding. But what does it actually mean to solve it? Well, in the world of quadratics, solving means finding its roots. These solutions, or roots, are just the special values of x that make the whole equation work out perfectly, that make it equal 0. And here's the really cool part, where the numbers meet the picture. The roots are literally the exact spots where that parabola curve crosses the horizontal x-axis. It's the same thing. So how do we find these roots? There are a few ways for sure, but there's one master key that can unlock any quadratic equation you throw at it. It's the one and only quadratic formula. And there it is. Yeah, I know. It looks like a beast, right? Super intimidating. But I promise you, it's not as scary as it looks. It's really just a recipe. You just take your A, B, and C numbers, you plug them in, and this formula spits out the answer. Every single time, no exceptions. Okay, section 5, the formula's crystal ball. This is cool. Before we even do all the math, there's this one tiny magical part of the formula that can basically predict the future. It's like a crystal ball that tells you what kind of answer you're going to get. It's this little bit right here, the part that's tucked inside the square root, b squared minus 4ac. That's called the discriminant. And all you need to know is its value. Is it positive? Is it 0? Is it negative? Because that one piece of information tells you exactly how many times your curve is going to hit the x-axis. So if that discriminant turns out to be a positive number, it's simple. You're going to get 2 different real solutions. That means your parabola crosses the x-axis in 2 separate places. What if it's exactly 0? Well, then you only get one real solution, Picture this. The very tip of your parabola, the vertex, comes down and just kisses the x-axis at one single point. That's it. And the last case, what if the discriminant is negative? Well, think about it. You can't take the square root of a negative number, right? Not in the real world anyway. This means our curve has no real roots. It just floats there, completely above or completely below the x-axis, never touching it at all. And that leads to a totally different kind of answer, which we'll get to in just a sec. Okay, let's actually do one. Let's take 5x squared plus 6x plus 1 equals 0. Step 1, easy. Identify your ingredients. A is 5, B is 6, C is 1. Step 2, you just plug those numbers into the recipe, into the formula. Step 3, now we just cook. We do the math. The discriminant here is 16, which is positive, so right away we know we're looking for two answers. And finally, step 4, we split it for the plus and the minus, and there they are. Our two roots, x equals negative 0.2 and x equals negative 1. See, it's just a process. All right, section 6, when solutions get complex. So let's go back to that weird situation. What about when the discriminant is negative? When our curve just misses the x-axis completely? Well, this is where math gets really interesting, and we step into the world of complex solutions. So when we get that negative under the square root, we have to introduce a new character, the imaginary number I. And I is just defined as the square root of negative 1. It's a neat trick that lets us keep solving. So the square root of, say, negative 16 just becomes 4i. Your final answer will have a real part and an imaginary part. And here's the bottom line. A complex solution is just the correct mathematical answer for a curve that never, ever crosses the x-axis. That's all it is. Now, I know what you're thinking. That formula is a lot to remember. But there's a super simple trick that students have been using forever. You just sing it to the tune of Pop Goes the Weasel. Seriously, x is equal to minus b plus or minus the square root. Come on, try it. It sounds silly, but I guarantee you it gets stuck in your head and you'll never forget it. And really, that's what this is all about, having this powerful tool in your back pocket. We've cracked the code. You now know that from the perfect arc of a fountain to the shape of a bridge, it's the quadratic equation that's writing the story. It isn't just some numbers in a textbook. It's a fundamental blueprint for the world. So my question to you is, now that you can read the code, what are you going to see differently?